apologies for the slightly later than usual start. So today we're going to be discussing recurrent neural networks. This is the second lecture on these. In the reading notes, there's also a link to chapter 11 in the Goodfellow book. I believe it's chapter 11, which is kind of just general practical tips for deep learning. Highly recommend read that. Content from that is kind of scattered throughout, but it's a useful thing to read. And again, I've linked again these technical blog posts by Christopher Olah that are really nice, and I'm using some of the visualizations from, so highly recommend. We're going to go over the LSTM architecture today, this long short-term memory architecture. It's a little bit of a mouthful, all the equations and the architecture, and it's a bit to take in all at once. So this blog post, which I'm using the visualizations from, is super helpful. So, again, a place where I'm going to give recommendation for a particular suggested reading there. One other thing, which I meant to actually address on my courses, but was running late today, is that on the quiz, the first version of Quiz 7, for those who did it, there was this question about, could we run a neural network, or convolutional neural network, if we change the size of the images? And I said, but without changing the model at all? And the answer was no, but then somebody, said to me, well, couldn't we just downsample the images? And so I guess that's fair enough. So I didn't say you're not allowed to downsample, and so that's one where, I don't know, I'll be fair there. So it's true or false, everyone gets points for that one. So if you got 4 out of 5 or 3 out of 5 on quiz 7, now you get 4 out of 5. So again, I suppose I should have said without making any modifications to the images, but hey, give people credit for following up with these things. The other thing I want to just quickly clarify, this was something that had a couple people ask about after class, and I think it's partially due to the fact that the notation I was using in the batch norm slides was from previous versions of these lectures in previous years, but I just wanted to clarify with this batch norm idea, so this batch normalization. The key idea is that we're normalizing what's called the hidden unit activations. And by activations, just mean the values of the hidden units. So we take the input, we transform it by some linear function, and we get some hidden unit values. These are sometimes called the activations. And what batch norm is doing is within a particular mini batch, so say we have 256 examples that we're using in this particular batch, we're going to get what is the H1, the first entry of the first hidden vector for all those 256, get the mean and the variance of that, and that's what we're normalizing over. So we're normalizing these hidden layers over the different examples within a batch. And unfortunately, in the previous lecture slide, the X was used instead of H, which I think confused people about what we were exactly normalizing. So batch norm is normalizing the hidden layers. Okay, so that clarification out of the way, we're moving on now to talk about recurrent neural networks, talking about long short-term memories, which is a particular type of architecture, quite a famous architecture now. These days, really, RNNs are almost synonymous with LSTMs, and LSTMs were developed in order to solve this problem of modeling long-term dependencies in sequences. So we're going to talk again with this motivation of language modeling. This is a very classic traditional application of RNNs, where what we're trying to do is we're looking at some sequence of words. We want to predict what word's going to occur next. Now, suppose we have an input paragraph, a relatively long paragraph where it says, I grew up in France, I worked at this particular restaurant for 10 years, blah, 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 and then at the very end, it says, I speak fluent French. Now, we want to predict that this word French is going to occur, but this is going to be kind of hard because by the time we get to speak fluent French, we've talked about working at a restaurant, maybe we talked about, I spent summers by the ocean and all of this. Nothing has anything to do with France or being French. That information was right at the beginning of the sequence. So it can be challenging for these sorts of models to maintain, to keep information around about these long-term contexts. And a bit more formally, so that's kind of an intuitive definition of kind of modeling long-term dependencies. It can be hard, but why is this actually hard in terms of optimization? So why do regular recurrent neural networks, so these Elman or these Jordan RNNs that we talked about in the last lecture, why do they struggle with this? Well, really, mathematically what happens is this issue of what's called vanishing or exploding gradients. So the key intuition here is just what we're doing is we're multiplying this weight matrix, W. And I'll also say that I apologize, you can't see my pointer on the slides, but I like to walk around and use my pointer, and so it's one of the benefits of coming to class. I apologize that there's no way to have a nice pointer on there that allows me to still move around. But yes, so standard LSTM is we're applying the same W matrix over and over again, right? If we unfold our LSTM, we get something that looks like a feed-forward neural network, but we don't have different W matrices. We have the same W matrix. You can kind of think that what we're doing is we're multiplying the same thing over and over again. And if we think in a simple case where W is just a scalar and not a matrix, what we're doing is we're kind of multiplying something over and over again, which is like raising something to a power. And say you raise, a value to a power k, and as k grows big, this number is going to either blow up. We're going to have an exponential explosion if W is greater than 1, and it's going to go to 0. It's going to vanish if W is less than 1. So when we're multiplying the same thing by itself over and over again, and we do this, say, 50 or 100 times, even kind of a number that's just slightly less than 1 is going to really shrink. If it's bigger than 1, it's going to blow up. Now this is in the context of just scalars, but again, it's also important to think about this in terms of the way that backpropagation works and the way that these recurrent neural networks are optimized. So remember in our backpropagation lecture, really what we're computing when we're doing backprop or stochastic gradient descent, we want to know, if I change my input by a small amount, how does that change my output? That's basically the intuition of what we're doing when we're computing derivatives. We're saying, if I change my input, how does my different parameter values impact my output and my loss? But now if we have this issue where we have the same thing being multiplied by itself all the time, this means that little changes at the input can lead to big changes at the output. It makes it really unstable for computing losses. You also have an activation function. So yeah, the question there was, don't you have an activation function? And this is true. And in fact, the mathematical intuition I'll expand on a little bit more here is easiest to talk about when you don't have an activation function. So empirically this happens, but the mathematical intuition that people give for this vanishing gradient problem really simplifies things and says that let's not worry about the fact we have a sigmoid or a tan H activation function. Those can help a little bit, but they don't totally solve the problem. The problem is still just that we're multiplying something by itself. We have this multiplicative interaction that's happening over and over and over again. So pretend for a moment that we're living in a simple world with no activation functions, just to give a bit more concrete mathematical intuition for what happens when we're multiplying a matrix by itself over and over. So we have a simple linear RNN. So this is an RNN which is just the hidden state at time step t is equal to some weight matrix W times the previous hidden state. There's no input, there's no nonlinearities. Now, from standard calculus, or algebra, we can compute the eigendecomposition of this. So we can represent this W matrix as an orthogonal matrix times a diagonal matrix of eigenvalues times an orthogonal matrix. And then if we think about unrolling this linear recurrent neural network, what we're going to end up with is to get the hidden state at time step t, this is going to be this W matrix to the power of t times the initial hidden state. And if we can unroll this using the eigendecomposition, it's going to look like this. And then the important thing to note is that since the eigenvectors are orthogonal matrices, Q transpose times Q is the identity. It's an important property of orthogonal matrices and eigenvectors. So what this means is that in the end, what we get in this kind of simplified linear world is that the hidden state at time step t is going to be some orthogonal matrices we don't really need to worry about, but it's going to be this eigenvalue matrix. So this is a diagonal matrix. It's got the eigenvalues of W on the diagonal, and it's going to be raised to the power of t. And the intuition here is that this means that if we have some large eigenvalues, those things are going to blow up. If we have small eigenvalues, those things are going to decrease. And in fact, even though this is based on a simplified world where we don't have activation functions, when people were really faced with this issue of vanishing and exploding gradients before LSTMs really became the norm, people would actually look at the eigenvalues and would actually try to normalize things. And in fact, this was the case, that if you actually try to initialize your W matrix in a way such that its spectrum, so its eigenvalues, were kind of nice and right around 1. So this is a serious issue. And again, the intuition here is that we're multiplying a matrix by itself a whole bunch of times. This is going to end up exploding if we have large eigenvalues and going to 0 for small eigenvalues. So that's the problem. The problem is that we can't just run naive Elman RNNs because they're really hard to train, they're very unstable, and after, say, 10, 15 time steps, things just don't really work. So how can we solve this problem? Well, the simplest way to solve this problem is just by what's doing called gradient clipping. So gradient clipping solves what's called the exploding gradient problem. The vanishing gradient problem can then just be solved by initializing in such a way that you don't have really small eigenvalues. But gradient clipping is a pretty simple idea, and in fact, even though we're going to talk about a better way to have stable recurrent neural networks, gradient clipping is still a general approach used in deep learning. And the idea is basically that we just add a little if function in our stochastic gradient descent where we say if the gradient is greater than some threshold, well then we're just going to kind of cut the gradient off and just set it to the threshold times the size of the gradient, times the sign of the gradient. So basically this just means that we have some cap on how big our gradients can be. Yes, yeah. So this is a good point. So like, does this really solve the problem? This doesn't really solve the problem because you still, if you have really exploding gradients, then this is going to mean everything is just going to end up being threshold times sign of the gradient, and it's not truly going to solve it. This is true. So this is not the solution I would recommend for LSTMs. Gradient clipping is still useful actually to avoid, say you had just one training example that was really crazy, and then that could lead to a big parameter update that gave you, so like infinite values and gave you overflows. Gradient clipping can be a useful thing for stability in general. And it was initially motivated by trying to make things like Elman RNNs work, or at least that's where it became popular, but it wasn't the real solution. And in fact, the real solution is something quite a bit more complicated, which is called the long short-term memory unit. And I should say there's other competitors to the LSTMs, things called the GRU, which is the gated recurrent unit I won't go into detail on. The LSTM is the most popular, and really they all have this similar idea where what we're doing is, instead of just doing a simple RNN, so here's a simple RNN where we have our input, we have our previous hidden state, we have some nonlinearity, and these represent vector operations, like basically doing matrix multiplications and additions. And we're feeding it through a nonlinearity here. They use a tan H, could be a sigmoid. And then we get our next hidden state. This is the simple, basic Elman RNN idea up here. LSTM, we're packing a whole lot more into what's called the LSTM recurrent cell. So we don't just have this single update, we have all kinds of things going on. And it may look quite arbitrary about why is there all these things in this box, but we're going to go over all the components in this LSTM cell and discuss how they're actually motivated and useful for solving this vanishing gradient problem, but also intuitively these help your recurrent neural network, your LSTM network, kind of maintain a kind of dynamic memory, which allows it to keep information around in an adaptive way that's useful for making predictions from long-term contexts. Like that French example, actually keeping around some information about the fact that in the first part of the sentence, it mentioned France. So LSTMs are basically a variant of recurrent neural networks that are much better at dealing with long-term dependencies, and now we often talk about what's called the cell. There's also the cell state. We have a hidden state and what's called a cell state. We'll talk about these in detail, and oftentimes people call one of these blocks the cell. Now, the LSTM is governed by a set of update equations. So whereas the RNN was basically just one update equation, the LSTM is this fun batch of update equations here. So we're not going to just go over all this right now because it's much better to unpack all of this and understand what exactly is all this doing, why did we take what was a single update equation and turn them into 6 equations. So the first really core idea with LSTMs is this notion of what's called the cell state. So we had this hidden state of the RNN, which was this H vector, which was the vector that was kind of keeping around the information that we need to make predictions. The cell state's a similar idea, but the cell state, people often call it something more like an information highway, if you can call it that. But the important mathematical thing is that whereas the hidden state in the standard LSTM was updated in this multiplicative way, where the hidden state is the previous hidden state being multiplied by a matrix, the cell state is an additive function of the previous cell state. So we're still going to have a hidden state in LSTMs, but we also have this additive cell state. And the idea here is because we're doing additive updates are much more stable. You can do a whole bunch of additions and it doesn't blow up or vanish. We'll discuss what that multiplication is. So there is multiplications involved, but the main update equation itself is additive. And this particular multiplication here has to do with what's called the forget gate, which we'll get to in just a second. So yes, indeed, LSTMs have a lot of moving parts. There are multiplications involved, but a key design decision was having it so that the kind of core cell update equation is that the cell at time step t is an additive function of the previous time step. And how we actually compute that additive function is where all of the fun stuff comes in, and how we do that is using what's called gating. So the important things in the LSTM is that we still have a hidden state. Just like we had in an RNN, we're just adding a lot more things on top. So this hidden state, intuitively we can think of the hidden state in an LSTM as well as in an RNN as containing the information that we need to make the next prediction. The cell state is something a little bit different. The cell state is more like a little memory store that's saying, what information should I keep around because it could be useful in the future? That's why it's called a long short-term memory. It's keeping short-term memory for a long time. So this cell state is the short-term memory part of this. And really for regular RNN, we're implicitly expecting the hidden state to play both of these roles. The hidden state is a thing we're using to predict the current thing, like the current word and language modeling, and the hidden state is also the information that's being transferred to the next step. In the LSTM, we're adding the cell state that's more explicitly kind of keeping around useful information that's useful not just for the next prediction, but for maybe many possible future predictions. And then the key thing is that the way that we do all these updates within an LSTM is using what are called gates. So there's a number of different types of updates happening, but this gating idea is pretty important. And this gating idea is basically taking a sigmoid layer. So we get some vector that we feed to a sigmoid layer, and this gives us a vector of values between 0 and 1. And then we take this vector where we have a bunch of values between 0 and 1, and we do an element-wise multiplication with some other vector. And we think of that as gating, because these 0 to 1 values, if there's a 1 in a particular entry, this means we're letting all the information at that index through. If there's a 0, that means we're letting no information through. So basically, we're using a sigmoid to compute what you can think of as like a mask that's telling us how much information should be let through at this gate. That's the intuition, and mathematically how this works is it's taking a vector, putting it through a sigmoid, element-wise sigmoid. So we're doing a sigmoid function at each element in our vector, gives us a bunch of values between 0 and 1, and then we're multiplying this by some other vector to apply some gating to that vector. So what's the first type of gate that's really important in an LSTM? And this was actually, this particular piece that was mentioned, isn't that a multiplication? So what the forget gate is this is the gate in the LSTM that determines how much information we're keeping around from the previous cell state. So the first decision we need to make when we're trying to make the update to our cell state is we need to say, okay, what information from time step t minus 1 should we keep around for time step t and all future time steps? And this forget gate is going to be a function of the previous hidden state, as well as the input at time step t plus a bias term. And again, we're putting this through this element-wise sigmoid. What we end up with was this f vector, here. And then we're going to use this f vector, we're going to multiply it element-wise by the previous cell state, which is basically telling us what indices, what dimensions should we ignore or pay attention to. Again, if we have ones, that's stuff we're keeping around. Zeros, that's stuff we're forgetting. There's a very analogous gate. In some sense, it's called the input gate. So the forget gate's telling us what should we keep around from the previous hidden state, and then the input gate's telling us what stuff should we add to the cell state based on our current input. So here, totally analogous. Again, our input gate is a function of the previous hidden state as well as the input at this time step. Again, it's just standard neural network. This is going to be a vector here, so this is an element-wise sigmoid. And then from this input gate, this tells us what information do we want to keep around. And this is what's called the candidate cell. So this is another neural network applied to the previous hidden state as well as the input. And this is basically saying, okay, what this would be kind of the simple hidden state if it was a regular RNN. But here it's more complicated where we're saying this is the candidate values, candidate information coming from our input and our previous hidden state that we might want to incorporate into our cell. And what we're going to do is we're going to combine this with our input gate to update our cell. So this is our candidate information, and this is our gate that tells us what parts of that candidate information should we pay attention to. And then at the end of the day, what we end up with is to get our new cell state, this is going to be the previous cell state multiplied by this forget gate. So this is telling us, okay, what information should we pay attention to from the previous cell state? And again, f here is a vector. This is an element-wise product. These are both vectors. F is going to have ones in places we should remember and zeros in dimensions we should forget. And the input gate's very similar. We have some candidate new kind of information to incorporate in this cell. That's this C tilde. And the input gate's telling us, okay, what parts of that candidate information should we pay attention to? And it doesn't end there. We have one more gate. We now have the output gate. So the output gate is what information from the cell state do we need to make the prediction. So the output gate is, again, a function of previous hidden state in the input. And now what we're doing is we're using the output gate to tell us how do we take the cell state and turn this cell state into our hidden state that we're using to make predictions. So there's a lot of these kind of gating things involved, and you might wonder to yourself, are all of these things strictly necessary? No, they are not. So you can make variations of the LSTM where you don't necessarily have all of these gates. So the gated recurrent unit is an example of this, which is a very similar model. There's been a number of proposals of especially people trying to figure out what is the minimal number of things that we need. This architecture works surprisingly well, and the key thing I think that really makes this work is this equation here, is this idea that in addition to having our kind of standard hidden state here, we have this cell state where this cell state is this additive update compared to the previous information, where these gates involve complex functions that involve multiplications, but then as a whole, this update is just additive. And again, this allows the model to keep information around in kind of a long-term way, or a short long-term way. And it also helps to prevent this vanishing or exploding gradient problem. Great question. So the question is there a reason why sometimes we use tanh and sometimes we use sigmoid? So here I'm opting to use the notation as kind of well as the details in the original LSTM work as well as in this technical post by Christopher Olah where these images come from. So generally tanh here is a stand-in for an arbitrary activation function. You could use something like a ReLU or anything you want in there. But in cases where we're using the sigmoid, it's actually important that we're using the sigmoid because we want these things to be between 0 and 1. So TANH is pretty standard to use here, but TANH is basically just, at this time, was the in vogue nonlinear activation function. And people used sigmoid when they really needed it to be like interpreted as a probability between 0 and 1. In general, you're still going to use TANHs in a standard LSTM, but you could try other things. It's a great question. Oh, this is a really good question, and something that, honestly, is not just for LSTMs, but also for RNNs. So what do we do for our first, so for kind of C0 or H0, like what is our first hidden state before we have any input, or our first cell state before we have any input? In fact, there's differing opinions. You can just initialize it as 0. It's not an uncommon thing to do, or initialize it as a constant. The other thing you can do is you can have that be a trainable parameter. Like in some sense, you have this vector, this C0 vector, or this H0 vector, your kind of first hidden state, your initial hidden state, your initial cell state, and you can learn what that cell state should be. Yes, it's kind of like a bias, actually. I've found that it helps a little bit often to actually learn that rather than just initializing it as 0. I believe the default in PyTorch is just to initialize it as 0 as well as TensorFlow. Any other questions on the LSTM updates? Yep. What's the role of the cell state? So really, like the role of the cell state is really, it's this part of the, it's a complement to the hidden state where the cell state is able to ideally keep around information in a longer term. It doesn't need to change as fast as the hidden state, so the hidden state's being used to make the prediction at every time step, but the cell state, it's kind of a bit further removed from the prediction, so it, in principle, at least intuitively, should have the freedom to kind of store more long-term useful information. And the other important role it plays is this fact that we're using additive rather than multiplicative updates, which means that we're updating the cell state, say 100 times. That doesn't lead to exploding or vanishing gradients because those updates were all just additive. So it plays kind of an optimization role that is quite fundamentally important, as well as kind of an intuitive role that it's keeping around useful information that might not be useful for the next prediction, but maybe could be useful for the prediction 5 steps from now. Good question. So there's only kind of one information highway here. Could we add more? Yes, you could, and I don't off the top of my head of a particular work that kind of phrases it in exactly that way by adding multiple, another information highway. One straightforward way that people do that is by making a deep LSTM. So we talked about how we could stack RNNs. So you can also kind of stack LSTMs, of course, but then you can hook these things up in all kinds of ways. So in some sense, some deep versions of LSTMs, that's really exactly the intuition they have, especially if they're not just naively stacking them, if they're actually kind of choosing to do things in some kind of clever way where they're rewiring, say, this cell state can go up here and be split into another one. So indeed, I would say that it's the benefit of doing so is really going to be analogous to like the benefit you get by just making an RNN or an LSTM deeper, which is really just increased expressive capability at the risk of overfitting. Yeah, so that's a good question. So how do you kind of tune or decide what information to keep around? This is an interesting one, and this is probably like kind of the crux of the LSTMs is you don't need to tell it what to do. The LSTM should learn from the particular task how much it needs to keep information around. So I think really good example is say that you are working on a particular sequence modeling task where this is actually a completely Markovian process. So a process where you only ever need to look at the last time step. You really don't need any long-term information. Right? Then an LSTM is going to learn that basically it doesn't need to keep anything around. Ideally, the LSTM should learn, if you give it enough training data, this forget gate can always forget everything. But, that's not always going to be the case. You're kind of relying on the LSTM to learn that, but you think like language modeling, depending on the language modeling task and also the language, Some languages have kind of longer dangling dependencies than others in general. So, unfortunately, well, for better or for worse, there's no way for you to really tune that. There's no natural hyperparameter here that allows you to give that. Is it going to forget or is it going to keep things around? Because that's all determined really by the parameters of this matrix here, and also this bias term. But it's a good point. I think that the intuition and the hope is that it is learning to do the right thing, and this is, very much the nature of deep learning is that by increasing the complexity of these models, increasing their representational capacity, we have hopes and aspirations and intuitions for what they should do, but we no longer have knobs that we can turn in the same kind of precise way. Yeah, so the cell state is multidimensional. So the question is, can the cell state store kind of multiple types of information? Yes, indeed. So the cell state is whatever dimension you want it to be. Again, it's pretty standard for these things to be like 64, 128, or 256 dimensions. And in principle, you can think that every one of those different dimensions is representing different things. And in fact, you could have that combinations of dimensions represent other things. So indeed, it's in principle capable of maintaining information about a wide variety of things, and it's going to depend on your application task. If it's a very complicated task where you really require keeping around all kinds of contextual information, it's probably a good idea to have really large dimensional cell states as well as hidden states. So this LSTM architecture, despite the fact that I pitched it as really this solution to this vanishing gradient problem that was really at the forefront of people's minds, say around 2014, 2015. But in fact, LSTMs have been around for a long time. They were originally published in 1997, although I think there might even be an earlier reference from Schmidhuber on that. And so in fact, it's actually a bit of a famous thing where Schmidhuber, this author, Jürgen Schmidhuber, who's a really brilliant individual and often named kind of one of the kind of giants of modern deep learning. All the time people will publish things and come up with new algorithms, and it'll be a Schmidhuber paper from like 1992 that already did it. So it's kind of just an interesting, more of like a sociological thing. He was very much ahead of the curve. So these LSTMs had existed for a long time, but we didn't have GPUs, didn't have PyTorch, didn't have TensorFlow, didn't have ways of training these things. And so really, it was an interesting situation where it wasn't that we lacked the model, it was that we lacked kind of the engineering and the data and all these things to make it work. And then somebody recognized, or kind of the community as a whole recognized in, say, the late 2000s or just in recent years, that these LSTMs were really exactly what we needed to build RNNs that didn't have this vanishing gradient or exploding gradient problem that could handle these kind of longer term contexts. And then following on that, of course, people came up with other architectures that were variations on this idea, using gating and using information highways and cell states. But to be totally honest, really LSTMs have emerged as the norm, and despite the fact there are other architectures that do, maybe slightly better or slightly less parameters, LSTM is almost synonymous with RNNs in this day and age. And that might change. Again, there's also like sociological aspects to this. It's not that it's necessarily a better model, but it's really become the de facto standard for natural language processing. Okay, so we're going to take a step back. We're talking about LSTMs. Now that's the kind of the one major thing I wanted to talk about today. The other thing I want to talk about today is something called encoder-decoder models, or the idea of how we can use RNNs or LSTMs to generate data. And you might say, well, we already kind of did this in what we'll call language modeling, where this language modeling problem, what we were doing is we were taking some input, some words, and then we're trying to predict the next word in the input. So in some sense, we were kind of generating text. You can train a language model, and you can use it to generate realistic-looking text. Highly recommend. There's some great blog posts by Andrej Karpathy called The Unreasonable Effectiveness of Recurrent Neural Networks. They're a little bit, tiny bit outdated now, but they're very fun in terms of not just for RNN language models, but for other types of language models, like generating things that look like Shakespeare and things like that. So it's actually pretty interesting. But that's a relatively simple version of generation. So here we're just generating one thing in the future. And one of the biggest issues here is that the number of things we're generating, so the number of words we're generating, is always the same as the number of inputs here. We're always generating kind of one more word. We don't have a way of like generating an entire sequence based on our input. So that's what we're going to talk about now. We're talking about generating sequences with RNNs. Here I'm going to flip back and forth from using, say, RNN and LSTM a little bit. Generally, what they're called sequence-to-sequence or encoder-decoder models that we'll talk about now really saw most of their success after people started using LSTMs. But in principle, you could use any RNN for this. And so the challenge that we want to solve here is we want to take some input data, and from that input data, not just generate a particular label or generate a label for each part of that input data, each entry in that sequence. We want to take an input sequence, and then from that input sequence, generate a whole new input sequence. So when I say, why would we want to do that? Well, probably the biggest example is machine translation. So I want to take in a phrase, a sentence in one language, and generate a sentence in another language. Image captioning is another example, where there we want to go from an image and then generate a sequence from that image that describes that image. So generally we call these encoder-decoder, and in the machine learning, the machine translation setting, these are often called sequence-to-sequence or seek-to-seek models. So the way that we handle the seek-to-seek problem is, somewhat unsurprisingly, using two RNNs. So here again, just an example, what the challenge is that we're not just outputting sequences of a particular length. We want to translate I love the movie to, say, 3 different languages like French, German, and Dutch. Right? Things could be of varying lengths, all kinds of different things going on. So this is very different from my language modeling task. And how do we do that? Well, the basic idea is we have first what's called an encoder RNN. This encoder RNN is going to take our input sequence, and it's going to generate what we often call a context vector from this. So we can think that the encoder RNN is trying to take, say, our sentence in machine translation, and it's trying to represent, the meaning of this sentence into a single vector. So we have this encoder taking in the input and putting it into this C vector. And the C vector is usually just the final hidden state. And then we're going to use a decoder. This other RNN is going to take this context generated by the encoder, and it's going to use it to generate a new sequence. So let's unpack this a little bit. So this encoder model is really just basically a sequence classification, a standard RNN. We're just taking in our input sequence, and we're generating this context vector from it. Now there's a variety of design decisions here. Most commonly, the C vector is just the final hidden state of the encoder RNN. So we have some, say, sentence we want to encode, like I love the movie, and we feed this through an RNN, and then we take the final hidden state as our context. And again, using the example of machine translation, what we expect, or what we hope, what we want to train our model to do, is we want this C vector, this context vector, to encode all the information we need to generate the decoded sequence. So in machine translation, this should encode the underlying language agnostic meaning, the interlingua of this particular sentence. So the encoder is relatively straightforward. We basically already covered the encoder in the last 2 lectures. You could use a standard LSTM there. There's nothing special. But the decoder is a little different. So the decoder, at every time step, is going to take this context vector as part of the input. So it's taking the context that was generated by the encoder, using that as part of its input to generate what is the next word, what is the next entry in this sequence. But it's also going to take the output of its previous time step as the input. So if we're doing machine translation and we're doing, say, I love the movie, then in the first time step, we look at the encoded context and we say, okay, the first word is je. And then when we're generating the next word, which gets a little bit tough with French, where really we should have J apostrophe now, but what's going to happen is we're going to say, okay, let's condition on the fact that we already output the word je. And then what should we generate next? And so in this decoder LSTM, what it's taking as input at every time step is the context, kind of the global context. So what is the thing we're trying to generate in general, as well as what did we generate at the last time step. And we also hope that the hidden state, or the LSTM cell state, is kind of encoding the information of what we've generated so far. And usually, when we're kind of including both the context vector and the previous output, we're just concatenating these two things. But there is a lot of design decisions here, and I'm going to say this up front. I think I mentioned again in the lecture slides later on, but I'm going to discuss kind of standard encoder-decoder models, some standard variations of this. But this is by no means a statement that this is the only or the right way to do it. Now, and again, you think about LSTMs, all these gates, all these different design decisions. You could do concatenation. Sometimes you could multiply things element-wise together. You could average things. Generally, I'll talk about approaches that have been found to empirically work well and are common practice in the field, but that is not a statement that they are kind of normatively the right thing to do. And it's important to keep that in mind, because you don't want people to not explore things just because you thought it was the right thing to do because it said so in one of these lecture slides, and that's very much true when we get to this kind of deep learning, especially LSTMs and RNNs. So one minor point here is, well, now that we're generating a sequence that could be of any length, how do we know when to stop? It's a pretty simple idea. We just generate a special end of sequence token, and once we generate that token, we stop. But it's important that the model has to learn. If the model wants to learn to generate sequences of length k, it has to learn to count how many things have I already generated so far. And then once it's like, okay, I've generated k things, now I should generate the end of sequence token. And again, LSTMs are pretty important for actually having these things work. With standard RNNs, it's really hard to even make them count. So LSTMs are much better at these sorts of counting tasks, again, because of the cell state, this kind of information it's keeping around. And then you also might wonder, well, how do we train this thing? Well, again, we're just going to train it using backpropagation, and it's important to first think that we basically have, on the decoder, something that's a lot like the language modeling or the sequence modeling task. At every time step, we're generating a new word. And so in that sense, the training is going to be very analogous to how we trained language models, where we're going to have the fact that we're training a bunch of different classifications based on predicting all these different, say it's words in machine translation. So this decoder is being trained a lot like a language modeling or a sequence modeling, LSTM or RNN, but the important thing is that we're also getting information from this encoder, and the loss being computed here, the decoder, is being backpropagated all the way through into this encoder. So this encoder is also learning during training what is the right way to encode our input sequence into this context vector C so that our decoder can do well. So here again is a case where we're really sending information a pretty long way. So if we're trying to translate sentences of length, say 10 to 20 words, these are 40 length sequences, we want to actually have the learning, the signal be propagated all the way through this prediction task down here, all the way into this encoder. And again, a reason why having these LSTMs, having this good gradient flow is very important. That's a good question, actually. So the question is, why is C fed also into the Y vector? Those images are taken from a textbook, and so I will double check why that is, but I would say that's an unnecessary thing to add. Again, I think part of the reason you could say that, it's redundant, because, yeah, it's just redundant. It's not wrong, but it's redundant. It's a fair point, though. So generally, these images are generated using software based from the deep learning book, but that's not actually in the book. So I'll fix that if necessary. Yep. Oh, how does the loss function work? Yeah, this is a really good. So the question is, how does the loss function work? So how are we actually effectively training this thing? So part of this I'm gonna talk about here, but it's not exactly that issue. So for one, generally the loss function is that just like with language modeling, it's basically a classification task. But basically here we have 4 different classification tasks. You kind of think of them as that we're at any particular batch. We have 4 different, so this particular hidden state here is getting loss information from 4 different classifications, where this is just basically a classification loss, like a cross entropy loss. So in that sense, that's relatively straightforward, but one complication is, well, maybe you want to weigh certain types of errors more than others. That's a little bit tricky. It's pretty non-standard. People almost always will just have a standard, cross entropy loss at each of these, where we're trying to predict, say, if it's words, there's size of vocabulary possible classes to predict, and we get a 0 if we don't get it correct, and we get a 1 if we do, we get the negative log probability that we get for the correct answer. But things are a little tricky, and one particular thing that's tricky is that when we're training, so during training, you could think that, well, what happens if we're doing, say, machine translation, and we're saying we're translating I love the movie, and then for some reason the model gets it incorrect, and it puts the first word as tu instead of je, right? So it has just the wrong, it's using the second person instead of using the first person. Well, you think, okay, well, that's a mistake, but that mistake's then going to cascade, right? Because we're then going to feed in the fact that we output that tu as the first token, we're going to feed that in when we're trying to generate the next token, and we can have kind of cascading errors over time. This is the big issue, I think is related to the point that you're mentioning, and how that we deal with that is with a technique that's called teacher forcing. So teacher forcing is this approach where during training, we make a prediction for what the word at time step t should be, and then we get that right or wrong. But then instead of using our prediction and feeding that to update the hidden state or the cell state, we use the ground truth. So we don't use our prediction, we use what was the right thing we should have predicted. And we call that teacher forcing. Obviously at test time, we can't do that. We don't have the ground truth. And an important thing here is this leads to this disconnect between, during training, we're kind of helping our model out. We're kind of propping it up by saying, even if it's making mistakes, you got the first 2 words wrong, we say, okay, you got those wrong, we're going to give you some error, so you can backprop and do better, but we're going to tell you what you should have said for those first 2 words in the sequence. And something that's not totally common, but theoretically is the right thing to do, is that really you should kind of wean the model off teacher forcing. At the beginning, you should always kind of correct the model. It's making mistakes. It gets the first word in the translation wrong. You say, okay, that's an error, but now try and get the next word when we give you the correct first word, and so on and so forth. But then as training goes on and your model gets better and better, you start not doing teacher forcing. You might do it with a lower and lower probability over time. And there are some theoretically well-understood strategies for what's kind of good ways to wean off of teacher forcing. I should say, though, that despite the fact that that is theoretically, in some sense, the right thing to do, it's pretty common for people to just do teacher forcing during training, and then at test time, not do teacher forcing. Yep. So that, oh, I see. So, like, because the number of outputs. So, you mean because there's just 4 here? So each of these outputs, these y's, the dimension of those y's is fixed. So your output vocabulary is fixed. So say, it's easier to talk about this in the context of machine translation. So each of these y's is basically a word we're predicting. And so say there's 10,000 possible words. Really what we're predicting is a class, a value between 1 and 10,000, right? So that's fixed. We can't generate words that were not in our vocabulary. So that's fixed. But the thing that's not fixed is here we're generating a sequence of length 4. but there's no reason to stop at 4. The only reason we would stop at 4 is if our model generated an end of sequence token. Then we'd stop, but otherwise we just keep generating, and we can. So again, it becomes complicated from an engineering perspective, in the sense that ideally, if you want to be really efficient and do good, batching together matrix multiplications on a GPU, it's kind of good to know in advance how many matrix multiplications you're going to do so you can organize your computation efficiently. But now we don't know, right? It's kind of, in principle, our LSTM could keep generating forever. So in fact, generally the way that people would do things is they will also specify a maximum length, and also sometimes even use padding, where we always just generate sequences of length 30, and we say just cut off what was generated after the end of sequence token. This is like an engineering issue, but it's a good point. So our model in principle will always keep generating, but from an engineering perspective, that kind of indeterminism of not knowing when it's going to stop is a bit of a pain. This is a great question. So the question is, if in general, and the pitch, for early versions of neural machine translation was that this encoded context vector is going to encode kind of the underlying meaning, what people call the interlingua of this sentence. So in principle, couldn't we then use that same encoder and just train a new decoder for a different language? It does kind of work. And actually, it works reasonably well, to be honest. But it works better to train them both jointly. And it, of course, also is interesting things relating to how close the languages are. So, training one for English French and then doing English Spanish works a lot better than doing English Mandarin and so on. But yes, this is a very interesting point, and in fact, this idea of to what extent do these encoded context vectors encode kind of this general sort of semantic information is an open question, but it's also, I should say, that these days what's really popular in NLP is actually not even for machine translation. People just train encoders to do language modeling. So this is these models people may have heard. I mentioned even in slides these things called BERT. There's one called BERT, one called Elmo, and one called, can't remember the other name of one of the other popular ones. But basically, there's been a lot of excitement about these models, and they're currently really the state of the art in natural language processing. And all they are is we've just trained an encoder on the language modeling task on absolutely massive data sets with really, really well-tuned, huge architectures. They're not LSTMs. It's actually an architecture we won't cover in this course, but it's kind of an extension over top of LSTMs. It's a slightly different idea. But basically, people train this encoder just to do language modeling, and then with that encoder, you can get state-of-the-art results on all kinds of tasks. Like you can do translation, you can do trying to do logical reasoning, so can you predict whether or not one sentence entails another. Like you could say that, what's a good example? So, Jim walked into the room and took his shoes off, right? Something that's entailed from that is that Jim was wearing shoes. But you could say that another thing that's contradictory would be, say, Jim is wearing sandals. Jim was wearing sandals, or something that's neutral would say that, Jim likes pasta, right? So just training one of these encoders just to do language modeling can actually do really well on that task of predicting whether or not sentences entail each other, can do really well on sentiment classification, again, machine translation. So in fact, this intuition you're talking about is true, although it's not usually machine translation being the way that we're training these encoders, these general encoders. It's usually language modeling, actually, or some other setups. And honestly, there's a lot of debate right now about the extent to which the performance of these sorts of kind of decoder agnostic encoders is really just indicative of the fact that our tasks aren't that hard, rather than being that these models are doing something really amazing. But it's a really interesting point. Okay, so as I've been going over, an application of this is machine translation, and is this actually an application that people use these things for? Indeed. So currently, Google Translate does use neural machine translation. In fact, I'm going to cite his paper in a few slides, but is actually a former student at Stanford. He's not the only one. He's a big part of the effort there. So really, in the last few years, so people who graduated 3 or 4 years ago, were people who really helped take Google machine translation. Didn't used to be neural networks, but now it is neural networks. You may have noticed that Google Translate got better in recent years, but also makes weirder mistakes than it used to. And that's a feature of the fact that now neural networks are used. So, but you might wonder, well, is it just the standard LSTM that I'm talking about? Is that what actually is powering Google Translate these days? Not exactly. But I can give you a bit of an insight for what are the kinds of things that people do to increase the complexity and make these LSTMs work better. This is going to get us up to maybe 2016, 17-ish. It's not exactly what Google's doing now, to the best of my kind of guess. But still, this is going to give you a bit of an insight on how we go beyond what's called vanilla LSTMs to make more complicated LSTMs. So what are a few things we can do? Two simple things we can do if we want to have LSTMs that are more powerful. We just increase their size. We increase either the size of the cell state, the size of the hidden state, or we add more stacks of LSTMs. So we make deep LSTMs. It's a relatively straightforward thing to do, but if you want to have a really powerful model and you have tons of data, it's a natural thing to do. The other two things that are quite common and that I'll talk about in a little bit of detail is, for one, what's called making the LSTMs bidirectional, and the other is adding what's called attention. So bidirectional LSTMs, pretty much exactly as the name entails. There was a brilliant insight of why are we processing from left to right all the time? I mean, granted, we kind of read from left to right, but isn't there information coming from right to left? Might it be good to also just run the LSTM the other way? And yes, that actually helps a lot most of the time. So instead of just running a left to right LSTM, people often do what are called bidirectional LSTMs, or bi-LSTMs. And oftentimes when people say they run LSTMs, implicitly they're often using bidirectional LSTMs. So there really isn't too much in terms of math for how this works. It's really just running an LSTM both ways. And then instead of taking the hidden state from one LSTM, we can take the average, we can take their concatenation, so on. So that's relatively straightforward, but it's an important thing to note that there's no reason why you want to go left to right or right to left. You might then wonder, why are we even doing these things sequentially anyways? Why aren't we processing things in some more complicated structure? Why don't we use the grammatical structure of the sentence? Or why are we limited to doing these left to right or right to left? That's something that I will talk about in the very last lecture of the course when I talk about my research on doing a generalization of LSTMs to just graph structured data that can have any structure. But not for today. For today, the other thing we're going to talk about is attention, which is a very, very useful thing, not just for LSTMs. It's really become extremely prominent technique in deep learning. And attention is also, like bidirectional, quite intuitive. So how a standard encoder-decoder works, as we discussed, is that we take all this information, we encode it into this final hidden state, we use this as our context vector, and use this in our decoder. So the important thing here is that we're really just getting this one vector, the context vector, and putting it over here. Now, this is reasonable, but what if, in some sense, different parts of the output, so say in machine translation, different things we want to translate, different aspects of the thing we're decoding might depend more or less on different parts of the input. So in particular, if you think about you were doing translation, you would maybe be, paying attention to, certain parts of the input at different times. A really classic example of this is, say I'm translating something with somebody's name. Well, obviously, I don't want to pay attention to the whole context of the entire sentence when I'm just translating that person's name. I'm just basically copying their name. So I should really pay attention to just a particular part of the input. So the idea with attention is, instead of just trying to monolithically encode the entire context into one context vector, we're going to have it so that different hidden states in the decoder can pay attention to different parts, to different hidden states in the input encoder, depending on parameters that we're learning. So it's the basic idea that the decoder is allowed to attend or pay attention to different parts of the encoder. And the key thing here is that we're essentially getting information from all of the hidden states into our context vector. But the important thing is we're not just naively averaging these things. We're going to have the kind of way that we're using the previous hidden states at each part of our decoder depend on the kind of current thing that we're generating. And formally how this works is that the context vector at step S of the, I'm going to use S and T so I don't have the same T for both. So the context vector for step S in the decoder is going to be a weighted sum of the encoder's hidden states. And at different steps of the decoding, the weights in this sum are going to be different. So the context vector at time step S is a sum over all of the hidden states in the input in the encoder model, and we're multiplying by what are these alphas here that are called attention weights. And we have calculate different attention weights at each different step S during the decoding. And again, this is really a place where I'm talking about one particular kind of classic way of doing attention, but there is a wide variety of ways you could imagine tweaking this that work well and make sense. And where these attention weights come from is these attention weights are going to be a softmax, so we're always going to have these attention weights sum to 1. That's just a useful thing to do for stability, for example. And have the attention weights sum to 1. So they're going to be calculated through a softmax function where we have some score that's basically telling us, we're looking at the encoder hidden state and then the decoder hidden state, and we're saying, based on these two hidden states, how much should we pay attention to this encoder hidden state? And here, it's when we're generating the context vector for time step S, we're using information from the previous hidden state of the decoder because we haven't computed H subscript S yet. So what kinds of scoring functions? How do we actually compute, how much should we attend to one encoding hidden state given a particular decoding hidden state? There's a wide variety of things you can do. These are some examples from a paper by Tong Long, who, as I mentioned, is now at Google, previously a PhD student at Stanford. So simple thing you can do is you can just take dot products. You can do what's called like a bilinear model where we're doing a dot product but we're putting a matrix in the middle here. We could concatenate these two things. Sorry, that's a errant parentheses. We could concatenate these two things and feed them through a neural network. There's really all kinds of things you can do for attention. This one sometimes, I can't remember the name people use for that one. This is a pretty standard one though. So this attention idea is relatively simple in some ways. I mean, it adds complexity. So all of these things, in terms of drawing pictures, they're relatively straightforward. In terms of writing code, it gets more and more complicated. But as things have got more and more complicated, we've built up more and more of these modules that you can use. And really, you don't need to code LSTMs anymore. There's LSTM cells built for you in most standard libraries. But it's important to kind of keep in mind that we're kind of building up this complexity, and attention is not a trivial thing to implement, but you can think about this is all happening on top of all the complexity of an LSTM already. So if you were to try to code this by hand, it would be pretty difficult. And that's why I think an interesting point is that really a lot of these advancements we've been talking about in this lecture and also with CNNs were really enabled by this automated differentiation and these sorts of techniques, because we're allowed to kind of abstract away this complexity and come up with all these fun things like bidirectional LSTMs and attention that really would have been pretty crazy to try to compute gradients by hand for. And why is attention useful? Well, for one, it really empirically improves results. It also adds what can be thought of as a form of interpretability. So what's kind of cool is you can say, okay, during decoding, which parts of the input, which parts of the encoder are we attending to at different steps? So you can kind of look at this as, in some sense, telling us an alignment, as telling us which words in the output, when we're generating those words, what are we paying attention to in the input? So here's an example of French to English, where you can see for the most part, it's pretty diagonal, which means that, kind of as you'd expect, French and English word order is pretty similar. So when we're generating the fifth word in the English sentence, this is kind of attending to the fifth word in the French sentence. Although you can see here we have the reversal because adjectives replacement in French and English is reversed. So it's kind of cool, right, in the sense that LSTM's totally uninterpretable. Neural machine translation, one of the downsides compared to the previous approach, which was called phrase-based machine translation, is that in phrase-based machine translation, we had these phrase tables we could inspect. Now we just have neural network weights. So how do we know, why is this thing making these crazy errors? We still can't totally explain it, but this attention does give us some form of inspecting what this model's doing and allowing us to convince ourselves that, hey, look, it's doing a reasonable thing. The word order is pretty much linear, except for in the case where we have this flip due to, for example, the adjective placement. So attention is not just useful for sequence to sequence. Here I'm not going to actually discuss the complexities of the model. It's quite a complicated model, but you can also combine convolutional neural networks with recurrent neural networks to have attention over images. And then what you do is you use a kind of a convolutional neural network where you're learning to attend to different parts of the input image, using that to generate a context vector, that you then feed that context vector to a decoder LSTM that generates a caption for the image. So this is kind of basically what underlies state-of-the-art. This was 2000, the citation, 2015. Wow, it was even earlier than I thought, yes. So, but that's the basic idea where this attention isn't just useful for machine translation, but you can even use it in the context of convolutional neural networks. And again, this encoder-decoder idea is not limited to just machine translation. You can encode images and decode text from those images. Just to show you a few examples of what this looks like. So here we have a woman is throwing a frisbee in the park, and you can see this is visualizing what parts of the image the model's attending to. So you can see it's attending to the fact there's a frisbee being thrown. There's a dog is standing on a hardwood floor. It's attending to the dog's face, and so on. And so again, not only did this improve the empirical quality of the captions that were generated, but it also helps us kind of interpret a little bit what the model's doing. There's a few more examples, but in the interest of time, we'll skip this. I'll just say as one other kind of note on kind of what is frontiers of what we can do with these encoder-decoder models. So generating dialogue. So dialogue is a very challenging task. So trying to actually build AI agents that can hold reasonable conversations. So you want to have, a machine learning agent that could play the role of, say, speaker B here. And things get quite complicated because, in this case, we no longer have just simple LSTMs anymore. Now things can get crazy. I won't go into details, but this is actually work that was done a couple of years ago by Joe Pinot's group here at McGill, where we want to, if we're trying to hold a reasonable conversation, it's not just that we're generating individual, utterances. We also want to, keep around some information about the global kind of conversation context. So the way that they do this is they actually have a hierarchical LSTM. We have one LSTM that's maintaining the kind of conversation level information, and then at each step of this high level LSTM, we're using the kind of hidden state or what's generated by that high level LSTM to run a lower level LSTM that actually generates the particular utterance at that step in the dialogue. So not something I expect you to know the details of, but just to give you a sense of what are the ways in which people kind of are combining and messing around and doing really cool state-of-the-art research with encoder-decoder models and kind of deep learning in general. And here's just a few examples of what some of the dialogue can look like. This is all taken from slides by Ryan Lowe, who was a co-lecturer for this last year. And so you can see, some of these things, it's kind of reasonable. It's like the sun is shining, I know something. And these are actually cherry-picked. It's actually a thing where dialogue, despite the fact people can show some pretty cool demos, it's actually really hard to do right. And in fact, a funny problem that we're getting a little bit better at, but that is one of the big issues right now, is these models really love to just generate I don't know. And other kind of utterances, because they're really it's a really low risk thing to do. Is just to generate these utterances that don't really have any meaning and just say yes, maybe, and things like that. So This is a challenge, and a big challenge with this is how do we automatically, what's the loss function here? So this is where things get really hard, is that the reason why dialogue is not trivial, well, it's trivial, a lot of reasons, but one of the big reasons is that there's no straightforward way to say, oh, you get a +1 for this utterance, or you get a +2 for this one, it was slightly better, unless you had a human sitting there and rating things every single time. But with the amount of data we need for deep learning, it's not possible. So this is a really interesting open research area. And with that, we'll call it for today. So you should know vanishing exploding gradients, LSTMs, encoder decoders, and definitely, conceptual understanding of this attention idea.